Hello, this is Dr. Viv. Let us discuss the scalar triple product of three vectors. So suppose you had three vectors, each living in three-dimensional space. That's what R3 means here, with coefficients that multiply the vector to increase or decrease its length coming from real numbers. That's what the parenthesis means. And each of these vectors, you know already that you can do two kinds of products, the cross product and the dot product. Well, suppose you have created a cross product already, and so you have a new vector. Can you maybe take that new vector and dot it with another vector to create a scalar? That's the natural way to create a triple product between three vectors, and that's exactly what the definition tells us. So suppose we had three vectors A, B, and C. Then the definition of the triple product is that this is equal to A dot B cross C. Now remember our study of the cross product earlier. In the earlier videos, we talked about B cross C as being written in terms of a determinant. So assigning A components AX, AY, and AZ, I get AX I hat plus AY J hat plus AZ K hat dotted with B cross C, which I can write as I hat, J hat, K hat, and then BX, BY, BZ, CX, CY, and CZ. So that's, you immediately realize that when you take the dot product, the I hat and the J hat and the K hat terms will interact, and so you end up getting the following determinant with X component, Y component, and Z components of the vector A in the first row, and the same for vector B in the second row and vector C in the third row. So that's the definition of the cross product. Now observe that the determinant will not change sign. It changes sign each time you interchange the row or column, but if you interchange the row or column twice, it does not change sign. So the cross product, the triple scalar product, has the symmetry, and I can think of it as a symmetry that can be expressed in the form ABC. Now if there's no risk of confusion, I like to omit the commas in between, is the same as BCA, and that's the same as CAB. What this represents is what I just told you. You can interchange two rows or two columns without affecting the result. Now, in the cross product video, I ran out of time, so I could not tell you the geometric meaning of the cross product, but this is a good time to dwell on that. The geometric meaning of the cross product is that it is the oriented planar area of a parallelogram formed by B and C. So if you try to picture this by drawing a brief sketch, this is how it would look. If I had the vector B and the vector C, now this is going to be a three-dimensional sketch, so I apologize in advance for any confusion. So B cross C is perpendicular to both B and to C. That's the nature of the cross product of two vectors. But what is the magnitude of B cross C actually represent? It turns out that it represents the area of this parallelogram. Now what's a parallelogram? You just have to create a side that's parallel to B on this side and a side that's parallel to C on this side. So that's a parallelogram, and the area is just this area. Now if you think about it, if the angle made between B and C is theta, then the magnitude of the cross product is also given by, I'll indicate the magnitude by putting this double vertical brace like that. It's given by the magnitude of B times the magnitude of C times sine theta. Well, you can see that that clearly gives you the area of this parallelogram. For example, if theta is 90 degrees, B and C are perpendicular, and this just tells you the area is that of a rectangle, length times width, B times C. So this certainly, the interpretation certainly makes sense. Now oriented, the word oriented comes from the fact that it's got an area element to it. And that area element is given by what's called the right-hand rule. If you take your right hand and start from B and go into C in the only possible way that you can curl the fingers of your right hand, then the thumb gives you the direction of B cross C. That was one of the interpretations of the cross product, the first interpretation, and then we found that that interpretation was unwieldy to use. But we're going to use this to understand the meaning of the triple cross product. So the oriented aspect of the area comes from the n hat vector here. So it's an oriented area. It's an area with a direction. And this is the part that's kind of new. So when you dot this vector with now A has got to be some vector for this not to be 0. A has to be a vector that's not in the same plane as B and C. If it's in the same plane as B and C, the dot product of A with B cross C will be 0, because if A is somewhere here, for example, then that A vector, when you dot it with the n vector, will give you 0, because cosine of 90 is 0. So you have to have some amount of sticking out involved for the A vector. So a portion of the A vector sticks out of the plane formed by B and C. So we'll draw it like that. If that A vector is like that, it's going to form some other angle with the vector B cross C, and let's call that angle something like psi. And so now we have a full-fledged interpretation of the triple cross product in terms of all these things. So well, I don't really need to write the magnitude anymore, because the magnitude of the triple cross product is just the triple cross product itself. But it takes into account the fact that I don't consider plus or minus to be a problem. So I'll just write it like this. A, B, C. Well, that's going to be ABC sine theta cosine psi. So that gives us what's called the volume of a parallelepiped. Just as you have a parallelogram here, this is volume of a parallelepiped. So that's the geometric interpretation of the triple cross product. Now, going back to the algebraic matters, let's find a way to write the triple cross product so we can actually use it while proving identities. And we can use the Levi-Civita form of the cross product. Now remember, the cross product of B, let me write it off here, B cross C, the ith component of B cross C, was given by epsilon ijk bj ck. That's the way of writing it. Now Einstein summation is assumed for indices j and k because they're repeated. Now what does this give us? This tells us that this is none other than ai multiplied with b cross c I, because dot products are written like that. If you have a dot b, you can write it as ai bi, because that's a1 b1 plus a2 b2 plus a3 b3, with a convention that a1 is the same as ax A2 is the same as AY, and A3 is the same as AZ, etc. So if you're moving from XYZ to 1, 2, 3 here, when you use the Levi-Civita tensor. So now we have, let's substitute for this. So I'm going to get epsilon ijk ai bj ck. This is a completely satisfied monster because it's got three indices ijk and ijk here. So it's completely summed over and there's nothing left over. If there's no index left over, that means you have a scalar and not a vector. So that's one nice way of writing the triple scalar product. Now let's talk about some properties of the triple scalar product from an algebraic point of view. First, that it's trilinear. Any of these three vectors can be added to any other vector, and the cross product and the triple scalar product will decompose accordingly. So I'll write the trilinear property here. Suppose I have A plus lambda times D, where lambda is a real number, and I'm forming the TSP with B and C. Well, that's the same as forming the TSP first with just A, and then multiplying it by lambda, and then forming the TSP with D. You'll observe this sort of hybrid notation where I need to put commas, I put commas, because here it would look very awkward without a comma in between the vectors. You wouldn't know what's happening, but here there is no need for those commas. Then you have the usual properties like associative, and that comes directly from the epsilon ijk or the determinant properties, and I told you that already. The order of operations does not matter. That's called associative property, if you want to put a name to it. So one last item before we go ahead to the vector triple product in the next video is the utility of the triple scalar product in defining what's called the orientability or orientation of a coordinate system. Now, at first, some of these coordinate systems that we'll be encountering later are pretty hard to visualize and even think about in terms of ij and k. So what we can do instead is we can rely on this abstract notion. A coordinate system is said to be right-handed Now we're going to assume this is a three-dimensional coordinate system, although there are analogs for n-dimensional coordinate system. I'm not going to get into those. If the coordinate vectors, you think of ij and k, but we'll think of the more general basis. If you have a basis that's e1, e2, and e3, if this basis satisfies the following condition, if e1 hat, e2 hat, e3 hat, the triple scalar product is equal to +1. And left-handed if -1, if this is equal to -1. So I promised to earlier tell you this little secret about I hat, j hat, and k hat, and this time has now come for me to reveal that secret. So I hat, if e1 hat is the same as your vector I hat, and that can be represented as 1, 0, 0, because I hat vector has component x component 1, y component 0, and z component 0, and e2 is your j hat vector with component structure 0, 1, 0, and e3 is your k hat vector with 0, 0, 1. Then how are you going to find out? Let's do I hat, j hat, k hat to see if this is a triple, if this is a right-handed coordinate system or not. So we form the triple scalar product of this. I hat is that, and j hat and k hat. You'll notice immediately that this is none other than a unit matrix, and a unit matrix, of course, has unit determinant. So that's +1. So it's right-handed. If you write, it doesn't have to, the vectors don't have to be in any particular directions. So for example, I can have I hat in this direction, I can have j hat in this direction, and then by using my right hand rule quickly, I hat cross j hat, and so k hat has to be in this direction. So you can make up your coordinate systems in any octant.